All right, let's jump right in. Welcome to this explainer. Today, we're basically turning the factory floor into a classroom. We're going to master the setup, both physical and digital, of a seriously impressive piece of automation hardware, the Banner QS30EDVQ sensor. If you work in industrial automation, you already know that the gap between a sensor just turning on and a sensor functioning perfectly within a high-speed logic sequence is all in the configuration. And that is exactly what we're tackling today.
Here's the game plan for today. First, we'll meet the sensor. Then we'll wire up the 5-pin QD, decode the interface, run through the 3 teach modes, and finally, dive into some advanced setup configurations.
All right, section 1, meet the sensor.
So, this right here, this is the QS30EDVQ. It is a tough IP67 and NEMA 6 rated visible red beam sensor. What really makes this specific model stand out is that it's built specifically for low contrast applications. It literally sees what ordinary sensors miss. And that Q at the end of the model number, that just means we're dealing with the integral 5-pin M12 Quick-Disconnect version. That makes swapping it out on the fly an absolute breeze.
Now, before we wire anything or even think about powering this up, we need to talk safety. This is a critical warning straight from the manufacturer's documentation, and I cannot stress this enough. You can never, ever use this device for personnel protection. It doesn't have the self-checking redundant circuitry needed for human safety. If it fails, it could fail energized or de-energized. It's for automating processes, absolutely not for keeping people safe. Got it? Okay, moving on. Section 2, wiring the 5-pin QD. Let's look at the exact 5-pin M12 Quick-Disconnect pinout, because this really shows off how flexible the sensor is. Your brown wire takes a 10 to 30 volt DC supply, and the blue is your DC common. Simple enough, right? But check out pins 2 and 4, the white and black wires. This thing has bipolar outputs. That means you get one NPN, or syncing output, and one PNP, or sourcing output, active at the exact same time. You literally just wire whichever one matches your PLC's input card. And finally, pin 5, that gray wire, is your remote line. While you're wiring this up, keep a couple of strict limitations in mind. There's a hard 100 milliamp maximum load limit per output at 25 degrees Celsius. Exceed that and you're going to have problems. Oh, and remember that gray wire we just talked about? It's not just for remote programming. If you pulse that gray wire 4 times, you can securely lock out the physical buttons on the sensor itself. That is a real game changer for preventing accidental tampering by operators out on the floor. Okay, section 3, deciphering the interface. It's honestly kind of wild how much info they packed into this compact space. This visual interface is your absolute anchor. Up top, you've got instant visual feedback. The green LED tells you you've got power, and the yellow one lets you know when it's actively triggering an output. Dead center, you've got your configuration buttons, the dynamic plus and the static minus. But the real star of the show, that central 8-segment red bar graph. During your normal run mode, that bar graph acts as a real-time signal strength meter relative to your cutoff point. If you see 6 to 8 LEDs light up when your target is there, you are golden. That's an excellent, stable setup. 4 to 5 is good, but if you're only getting 1, 2, or 3 LEDs, you've got a marginal or unreliable signal. At that point, you really need to rethink your physical mounting, check your factory lighting, or look at your target contrast before trusting that signal to your PLC. All right, let's get into the fun stuff. Section 4, the 3 primary teach modes. We're kicking this off with the 2-point static teach. This is your classic go-to configuration. You use this when the line is completely stopped, and you can carefully present a target present and target absent condition right to the sensor. The sensor basically does the math for you, dropping a single switch point perfectly between those 2 taught conditions. And actually doing it is super straightforward. Just hold that static minus button down for 2 seconds until LEDs 5 and 6 start flashing. Present your first condition, say the part you want to detect, and click the minus button once. Then present your second condition, like the empty belt, and click it again. The sensor flashes a contrast level, locks in its threshold, and boom, returns right back to run mode. Done. Now, that works flawlessly in a static setup, but let's be real about the factory floor. What if your production targets are constantly flying down a high-speed conveyor belt? Stopping the whole line just to wave a part in front of a sensor? Not exactly practical or profitable, right? And that brings us to the second highly adaptable programming method, dynamic teach. This totally solves the moving target problem. To do this, you just press and hold the dynamic plus button. While you're holding it, let your moving parts and the empty gaps between them pass naturally through the beam. Once the sensor has seen both conditions cycle through a few times, just release the button. It actively calculates the perfect threshold on the fly. Pretty smart, right?
The third mode is single-point static teach, which you might know as window set. This one is absolutely perfect for highly consistent objects, like detecting a specific registration mark or an edge. Instead of finding a middle ground, you just teach it one single condition. The sensor then builds this strict, narrow sensing window right around that condition. Anything closer to the lens or further back in the distance is completely ignored.
Finally, Section 5, Advanced Setup Configuration. This is where it gets really interesting, balancing your speed with your environment. Out of the box, the sensor runs in normal mode, offering a 1.8 millisecond response time. In this mode, it actively blocks out crosstalk from other sensors and ignores fluorescent factory lights. But if you have insanely fast-moving parts, you can toggle it to high-speed mode for a blazing fast 300 microsecond response. But beware, there is a major trade-off here. High-speed mode completely disables crosstalk avoidance and light immunity, so only use it if you're absolutely sure there are no other QS30s nearby and your ambient lighting is perfectly clean.
Here's another powerful little secret hidden in the setup menu, the number 30. You can actually add a 30 millisecond off delay pulse stretch to your output. Why on earth would you want that? Well, imagine a tiny part shoots past the sensor at lightning speed. The sensor sees it, but the output pulse might be too fast for a slower PLC scan cycle to even register. By stretching that output signal by exactly 30 milliseconds, it acts as an absolute lifesaver. It guarantees your controller catches that count every single time. To get to these advanced features, you just press and hold both the plus and minus buttons for about 2 seconds. That drops you right into setup mode. From there, clicking either button cycles you through 8 specific parameter combinations. You can totally mix and match: normal or high speed, no delay or a 30 millisecond delay, light operate or dark operate, literally whatever perfectly matches your logic requirements.
And the best part is, you never have to guess where you are in the menu. You'll know exactly which of the 8 combinations you've selected by looking at the bottom 4 LEDs on that red bar graph. They are clearly labeled for you: HS for high speed, a little clock icon for the delay, DO for dark operate, and LO for light operate. Just click through until the lights match your recipe, hold both buttons for 2 seconds to lock it in, and you're back in business.
And that really hits the nail on the head as to why understanding this device at a deep level is so crucial. It's incredible how configuring this sensor properly bridges the gap between raw, messy physical motion and precise digital logic. So I'll leave you with this thought. The next time a fast object flies down the line and your PLC inexplicably misses the count, is it actually a mechanical failure, or did someone just forget to activate that 30 millisecond delay? Control of your automation line literally starts right here with the setup. Thanks so much for joining me on this explainer, and I'll catch you in the next one.